Hi, my name is Byoung Lee, and I'm faculty member at the School of Computer Science in Western Illinois University in Illinois. And thank you for coming to my presentation. I'm going to talk about extracting the significant degrees of attributes in unlabeled data using unsupervised machine learning. Okay, let me go to here. So first of all, why are we interested in this research is that these days unlabeled data is growing in greater volume and a very fast rate than labeled data. And actually, to use unlabeled data for machine learning, we need steps of appropriate data preprocessing. And normalization is one of the most popular methods to scale original data within the specified range of values. Uh, but actually, if the range of the attributes value are significantly varied, then normalization is really wonderful. I mean, because it balances the importance of attributes over the data. But the question is that, but if some attributes have a really significant impact on data clustering, for example, then isn't there any way that we can give a reward to that important attributes? So actually, we are interested in handling this problem so that we try to give kind of key role to that significant, attributes and try to see what kind of result you can have it. So that was the motivation. And this is kind of simple sketch is that when we have unlabeled, original data, actually, then we are not typically with the normalization process, then we can have scale data, so we can utilize this data. But here we want to go to one more steps to go. That is, we'd like to extract the significant degree of each attribute in the unlabeled data. So for example, if there are 10 attributes, we want to see the significant degree of each attribute. And then using that significant degree, we'd like to generate the weighted data so that after generating the weighted data, we are not trying to see how this weighted data is better than scale data, and of course, better than unlabeled data. So this is what we are not to do it. Okay. This is the procedure for the exploring the steps. That is, first of all, we need to decide the number of clusters by elbow method, very popular one. And then we're just gonna feed the data into a simple competitive learning network. This simple competitive learning network was the model that we used to extract the significant attributes so that we train using the simple competitive learning equation to here. And then after the training is done, we extract out here the significant degree of each attribute, and then apply that significant degree to the unlabeled data, and then explore the K-means clustering to try to explore, the effect of this weighted data. So we compare with the raw data, scale data, and the proposed or weighted data. Okay. How can you do that? First of all, here, this is a simple competitive learning network, which is kind of standard unsupervised learning model. And as the name implies here, it is very simple, learning model. That is, when you have input data comes here, then actually we'll find the winner output unit, and then we update the weights suppose I star is a winning unit, and then we just update weight J I star only for the winning unit. So for example, if this is a winning unit, then we only update connection weight from this first attribute to this number three, and second attribute to the number three, output groups, and here like this. So the reason it's doing this is that we want to make this weight I star vector closer to the current input vector, so that if in the near future, if the similar input pattern comes, then we want to make sure that at the same time, at the, the same output unit should be a winning unit, so that this is a learning algorithm here. That is, you say learning coefficient, and this is input data. This is corresponding weight. So this J represent this attribute, subscript here, and U that represent youth training patterns. So that after training is done, then we are interested in this weight Ji. So for example here, when you look at this weight, then this weight actually represent the strength weight between attribute J and clustering group I. So that when we have this equation Sj is a summation I weight Ji, then that can give us significant degree of each attributes. In other words, in this graph here, let me, cannot see the, okay, here. When you look at this attribute X3, suppose that when we accumulate this connection weight and this and this and this, accumulate these weights, then actually that can give us this significant degree of this attribute. So you want to see how this significant degree can change the original data set. So here, this weighted data set is a very straightforward way you can get it. That is, also here, J represent the corresponding attribute. U represent corresponding youth training patterns. So this is the original data by scaled down by normalization. And then this is the value that we get from training of a simple compatible learning. So after you got this, then you wanna explore to this very popular machine learning data set. That's a very long history data set, wine data set, iris data set, and the seed data set. So each data set have this number of attributes, and each data set has actually the input value of attribute continuous data set. So here, okay, where is my cursor? So here, this three data set, we tested, and the system was, Scikit-learn library to explore this K-means clustering, because K-means clustering is one of the most popular and the general clustering, techniques. So we want to explore the, general clustering algorithm with this very popular data set to see the result. So here, with the raw data, scale data, and proposed, weighted data. So here is, some kind of example of significant degree. For seed data here, this is the significant degree of seed data. And as you can see here, this attribute, compactness, and here asymmetry coefficient, and this length of kernel graph has kind of compacting attributes. Iris data, in this case, we are very interested in this data because you can see that the petal width in centimeter has very, strong, attribute, significant degree here. Wine data has the first and second attribute has good, significant degree. And this is the performance. That is, there are some improvements and the limitations here. For the raw data and scale data, weight data here, from scale data to weight data, this iris data and seed data, you can see that 4.7 and 3.4% increase. You can see that here from here and from here. You can see that there are some improvements here, but at the same time, as we can observe here that in case of wine data, there is not much big difference here between scale data and weight data. So here is some, you can find some limitations if there are not significant attribute in the data. And this is the detailed, performance result for wine data and seed and iris. So actually, this is kind of equivalent, tables. You can see that. So conclusion is that actually, we want to extract the significant degree of each attribute in unlabeled data set to see if it really works for efficient clustering performance. And so that this weighted data set, because it reflects the importance of each attribute. And we apply this to by Scikit-learn K-Means clustering, the popular one, to the very popular data set to see how it works. And there was, a good and bad result. Good is that there was some improvements there, but actually there is also some limitations. So I think to conclude, I think we need more data sets to be applied, and we should consider the parameters of weight significant factor to apply to make weighted data set from scaled data set. So this is kind of conclusion that we have right now. Thank you.